the definition of a derivative as a function, which means it has x's or variables in it, is the f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x divided by h. Memorize this. Everything has to be in exactly the right place. If h is approaching 0, h is the number you're dividing by. We've seen this in other examples. X plus h, f of x. So this is the basic definition of derivative, and you will see variations on this in case the question says, what's not true? You have to watch out for exactly how everything fits together. So let's look at a function. Say we have f of x equal to e to the x. And we want to find the derivative using the definition. So we want to find f prime of x, just as a function. So f prime of x is equal to the limit as h approaches 0. The notation says take your function and the input is x plus h. So that means the x plus h goes where the x is in the function. So it would be e raised to the power x plus h. And then minus f of x, which is just the function e to the x, divided by h. So this is what this looks like as the limit definition of the function for the derivative of e to the x. Okay. There's some algebra you can do to work through that and show that that works, but we're not going to worry about that right now. Let's go look at a different function. How about if I have f of x equal to 1 over x? Well, I do the same thing. If I want to find the derivative or set up the derivative, I use the limit definition, limit as h approaches 0. And here my function is 1 over x. So in place of the x, I put x plus h, and I'll have 1 over x plus h minus f of x, which is 1 over x, divided by h. So this is exactly what the definition would look like. I could make it wrong if I wrote it as the limit as x approaches 0 of 1 over x minus h plus 1 over x over h. I actually did several things wrong in this one. It's not x approaching 0 because the h is in the denominator. This should say h approaches 0. This should say x plus h because this is a positive h. And this should be a positive h. The plus is not right because it's minus. So this is not f prime of x for this particular function. So do be very careful that things match up correctly. Let's look at a little bit different type of function and some different wording. For this example, let's look at the function f of q equal to 1 over q plus 5. And we're not going to put this into the definition. The question involving this function says, is f of q differentiable at q equal to 5? Differentiable means has a derivative. So I want to know if I did take all of this function and plug it into the definition, and then I had q equal to 5, which would be my a value, a equal to 5, will that work? Well, let's first look at 5 in this function. Can I put in q equal to 5? Well, sure, that'll give me 1 over 10. Perfectly good number. That's generally what you check. If something works for the original function, it's probably true that it will work for the derivative as well. So here I'm just going to say yes. So let's look at the domain. 1 over q plus 5. I have to have a non-zero denominator. Always. That gives me the domain if I can get every value that does not give me a 0 in the denominator. So my domain here would be all reals except q does not equal negative 5. I cannot plug in negative 5. It gives me a 0 in the denominator. So if I back up and just say, is f of q differentiable at q equal to negative 5? That answer would be probably no, because you can't even put negative 5 into the original function. So it's likely that when you do the definition of derivative, you also cannot put negative 5 into the derivative function as well. With functions like this, it's a little bit more complicated to look for. If you have a linear function, straight line, f of x equals mx plus b. Now think about the derivative of a linear function. We've talked about linear functions numerous times. It's a straight line. It's got a constant slope. That means the slope's the same everywhere. So that the derivative is the slope of a tangent line, but if you have a line, the derivative is just m. The derivative is the slope, and it doesn't matter what x you have. So for a linear function, you have a derivative everywhere. It is differentiable everywhere. Quadratic, you're familiar with quadratic functions because the graph is a parabola. And if you think about a parabola in terms of slope of a tangent line, think about tangent lines, got a slope there, it's negative, slope there is negative, slope there is 0, positive slope, positive slope. There is not one place where you cannot have a slope of a tangent line. So for a quadratic, it's differentiable everywhere. So if you think about, especially with linear and quadratic, because you should be so familiar with those functions and their graphs, it's easier to sometimes answer questions like this. Is it differentiable at a point? This is a little more complicated, but for both of these types of functions, that should be fairly evident to you. You just have to pull in a lot of different information that you already know about these functions. Now let's take a linear function and use the definition of derivative on it. I'm going to use some different letters. Suppose f of p is equal to 8p. Now this is linear because if I had plus b, it's just b is equal to 0. So let's find f prime of p. Limit as h approaches 0. My f of x plus h would now be f of p plus h minus f of p divided by h. And I put in my function. So I'll have the limit as h approaches 0. F is 8 times p. So in place of p plus h will be 8 times p plus h. Minus f of p is 8p divided by h. Let's multiply out. Distribute the 8. I have 8p plus 8h, and then minus 8p. I didn't need to write the parentheses again. divided by h. And you will see that the 8p's are going to subtract out. I don't have those anymore. All I have is 8h over h. There's an h in each piece. The h's will cancel now. And so I'm left with my limit equal to 8. So that tells me that f prime of p is equal to 8. When you look back up at the linear function we started with, we said this could be considered 8p plus 0 so that you could see how it is linear. And the slope is 8. And we showed using the definition of derivative that the limit, thus the derivative, is also equal to 8. In this problem, we want to use the definition of derivative, the one with the limit, to find the derivative for this function f of t equals 5t minus t squared. We have the formula for the function, and let's use the limit definition to find it. So remember, the limit. Now, let me put the f prime up first. F prime of t is equal to the limit as h approaches 0 of f of t plus h minus f of t divided by h. You usually will see, instead of t, you'll see an x. For our problem, we have a t for the variable. So let's plug this in. Limit as h approaches 0. F of t plus h says wherever there is a t in the problem, put t plus h. So we are putting that into the formula. 5 times t plus h minus t plus h, that whole quantity to be squared. And since I have a bigger piece here, I'm going to include the square brackets around that so that all of that is f of t plus h. And then I will subtract off f of t, which is this exact 5t minus t squared. And all of that over h. So let's see if we can multiply all this out. Limit as h approaches 0. Keep my square bracket. The 5 I will distribute, so I have 5t plus 5h minus. Now, I have t plus h to be squared, that is t plus h times t plus h. So that will be t squared plus 2th plus h squared. And I needed to write that in parentheses because I have to subtract and distribute that with each term. Then minus, and if you want to subtract here, I'm going to keep it in a bracket for now. But if you subtract now, you don't forget to change signs. All of this over h equals the limit as h approaches 0. I'm going to go through and remove parentheses and brackets, so I just have a whole string of things up here now. I still have the 5t plus 5h. Now it's minus t squared minus 2th minus h squared minus 5t plus t squared, and all of that is over h. And happily, things will go away. I have a 5t here and a minus 5t here. I have a minus t squared here and a plus t squared there. And looks like everything else that's left has an h in it, which is what should happen. So when I come down to this line, what I want to do, I said everything that's left here has an h in it. I'm going to factor out an h. What's left here is a 5 minus 2t. And when I pull one h out of h squared, I have one left over h. Now notice I did not just say, let's cancel this h and this h. You can't do that because of the subtraction of the other terms. But now I can cancel those two h's. And I have the limit as h approaches 0 of 5 minus 2t minus h. And remember h approaching 0, we saw some of those examples of h's getting smaller and closer to 0, 0.1, 0.001, 0.00001, whatever. If I keep plugging those numbers in for h, it's basically the same as just plugging in a 0, and now I can't. So if I let this h become 0, I am left with 5 minus 2t, and that would be the derivative. That is f prime of t. So there's a formula for the derivative using this limit definition. The derivative of a function comes from the slope of a tangent line. Leibniz notation is a different way to write the derivative based on the form for a slope. Usually when we first start talking about derivatives, we write the derivative f prime of x. But that did come from looking at slopes of secant lines, delta y over delta x, slope of secants. And then we let the slopes approach the slope of a line that was the tangent line. So our derivative is actually the instantaneous rate of change in the slope of a tangent line. So when we think about the slope of a tangent line, the notation delta y over delta x is okay, but we can use a better notation that is exactly the slope of the tangent line, and that is the Leibniz notation. So f prime of x can also be written as dy dx or df dx. The d stands for the delta, for the change, but it is specific to the tangent line. So it is the instantaneous rate of change of y with respect to x. Now I'm going to say of y with respect to x because the rate of change of y is the rate of change of the function, and the function name is always on top. With respect to x, x is the variable name. The variable is always on the bottom. It's not dy over dx. It is dy dx or df dx. And that's the same as f prime of x. This is the Leibniz notation. We can also use Leibniz notation with higher order derivatives. So if this is our first derivative, if I want to take the derivative of the derivative, f prime of x prime, that gives me the second derivative, and I need a corresponding notation for the Leibniz notation. So the y here is what's inside here, the derivative. So let's see how that's going to work. Second derivative will be the derivative of the function, which I can call f prime or dy dx, with respect to x, which is a very messy fraction, which we tend to work with messy fractions sometimes. So in place of the y or in place of the f, I can put dy dx or df dx. But we don't really write it like that. We have a better notation. I have two d's right here, the derivative of the derivative. So I write it as d, and I put the second power up there, but it's not squared. It just means I've done the second derivative of y. And I've got with respect to x here and with respect to x here. So I write that as dx to the second. And it's not really x squared, but it does mean I took the derivative with respect to x once, and then I took the derivative with respect to x a second time. So this is the Leibniz notation for the derivative with respect to x of y twice. Now, if we want to look at the notation at a particular point, we have to go back up to our f prime notation. And if I'm talking at a particular point, at a point where x is equal to a and y is whatever y is, this notation is f prime at a. That's the way we write it. A is a particular number. The Leibniz notation for the first derivative would be dy dx at x equal to a. And this is similar to what we would do for the second derivatives. F double prime at a, or the d2y over dx2 at x equal to a. So the notation is exactly the same for higher order derivatives as well. The x means, in general, what's the formula for the derivative. The a means you can find the formula, but we also need to know it at a particular point. So these two are numerical values and not functions. We're going to look now at higher order derivatives. We know that f prime of x is the derivative of f of x. That's the notation that we use, f prime of x. Well, when I take the derivative, I get another function. So I can take its derivative. So think about taking f prime of x, and then let's take the derivative of that. So if I use the notation with the limit definition, I would be taking the limit as h approaches 0 of f prime of x plus h minus f prime of x divided by h. So this would be the limit definition, but my function is f prime. So this f prime prime is actually f double prime of x. I have another function related to the derivative of the original function. You can do this with any function. I can continue and have a third derivative, f triple prime of x, and so on. So that higher order derivatives will have a place in some of what we do later. But just keep in mind that the derivative is a function, so we can take the derivative of that derivative. And we have the third derivative. F double prime of x is the second derivative. We don't work a lot beyond second derivatives, but there are occasions when we might need to work with a third derivative. So, and once you get into derivative rules, you'll be doing more of these. Okay? We don't do them as much with the definition. Okay? Now we're going to look at the graph of a function here, and from it, get the graph of its derivative just using our derivative values or slopes of the tangent lines. When we look at the function, we see that if we start here, and remember we read from left to right, we start here and the function is rising. So I'll say it's rising, or we can also say that it increases. After we get up here, the function starts to fall. So going down here, the function is falling or decreasing down to about this point, and then the function begins to rise or increase again. Okay? So when you think of the function, think of it in terms of words. Rising, falling, increasing, decreasing. When we get to the derivative, when we talk about the derivative, we're going to talk about numbers. So when we talk about the derivative of our function, we'll do numbers because those are the slopes of the tangent lines. So let's look at what the numbers might be here. This looks pretty steep. So if I have a tangent line here at that point, my tangent has a big positive slope. So the number is a big number and it's positive. As I move up here a little bit, and I look at a tangent line there, my slope is not as steep. So let's say a small positive number. When I get to the very top and draw a tangent line, this is supposed to look horizontal. I'm just telling you in case it doesn't. A horizontal line, the slope is equal to 0. So we have slope 0. And then we start down the other side where we're decreasing. We have a slope of a tangent line there, slope of a tangent line down here. And if you look at the slopes, this one is not as steep as this one. They are both negative slopes. So let's say small negative. And down here, I'll call that a big negative for the slope. And I get down here, and here we are again with a horizontal tangent line where my slope is 0. Say slope equals 0. There we go. And then we start all over again. I start to rise. It's increasing. Up here, my slope is positive. Up here, it's positive and steeper. So I'm back to a small positive, and up here, big positive. And so the slopes are the derivatives. They're numbers. So let's go down and look and see how those numbers fit on a graph for the derivative. So when I look at my axes this time, this is still x, but these values I'm looking at are f prime of x. The slopes are the derivative, and so that tells me positive or negative. So first, slope equal to 0. This is what you want to do, the very first thing. Check where the slopes are 0. I had a 0 slope here. And if the slope equals 0, that value equals 0, which means it's on the x-axis. And I have one here, whatever that x value is, right here. So those are the two places where the slope is 0, so the derivative is 0. Right along here. To continue, rising. My function was increasing, that was the word. The slopes were both positive. So to the left of this point, I have positive values which are above the x-axis. Well, I don't know what they are, I'm estimating. So these are where I had positive slopes. So slope positive. Up here. Decreasing, I have negative slopes. Remember how I got negatives until I got down to this point? So all along here, I have negative slopes, which means they are below the x-axis. So slope equals a negative, all down here. And then when it started to rise, we had positive slopes, so we're going up here again. And so up here again, my slope is positive. So everything that is above the x-axis, I have positive slopes. On the x-axis, I have 0 slopes, and below the x-axis, I have negative slopes. So the slope is the same. You can just say derivative. Derivative is positive, derivative is 0, derivative is negative. Now, the derivative is a function. So how about the second derivative graph? Let's see what I get from the second derivative graph. Let's come over this way a little bit. X, f double prime of x. And we're going to look at the slopes again. And if I look here, remember number 1, look at 0 slopes. That's going to be down here somewhere. I made a really big dip there. But this is where it will be 0. So I need my point about here. The slope of the first derivative is the derivative of the first derivative is the second derivative, equals 0 on the axis. This is now the function, so the word goes with the function. This is falling or decreasing. Remember that when the function was decreasing, we had negative slopes. So for the derivative of this now, decreasing for the function means negative slopes, means my slopes are down here, below the axis. Increasing, positive slopes. So on this side, I have positive numbers for the second derivative values. I could continue, take the derivative of another derivative and keep going, but I have the function, I have its derivative, and then I have the derivative of the derivative. So you simply continue to do the same thing. Check 0 slopes, put them on the axis. Check a 0 slope, put it on the axis. Increase, above the x-axis, positive slopes. Increase, above the x-axis, positive slope. Decrease, below the x-axis, negative slopes. Decrease, below the x-axis, negative slopes. So you continue to look at zeros and plus and minuses. Those are the numbers for the derivatives when you're trying to find the graph.